How's it going, everyone? Today we're going to start learning about one of Python's most popular and powerful libraries, NumPy, which is also known as numerical Python. NumPy is used primarily for fast and efficient numerical computing, especially with large multidimensional arrays and matrices. The very first step to using NumPy is installing it via pip in the terminal using pip install numpy. So here we'll type in pip install numpy. I already have it installed, so it's going to tell me that the requirement is already satisfied. Then we can import it using import numpy as np. Now, np is the naming convention we always use for NumPy. Please stick to this as it makes it much easier to share your code with other developers. Now that we've installed and imported NumPy into our project, let's move on to arrays. What exactly is an array? The NumPy docs define an array as a structure for storing and retrieving data. And arrays can be of different dimensions. For example, we might have a vector, which will equal a NP array that contains a one-dimensional array. 1, 2, 3, 4, 5, and 6. This is one dimension. A two-dimensional array, which is also known as a matrix, will look like this. As you can see, we have some nested data. Hence why we consider it to be of two dimensions. Also, when we print this vector and we print the matrix, what you're going to notice in the console is some interesting formatting. The vector is just going to look like a simple list, but you will recognize it as a NumPy array because there are no commas anywhere. And the matrix will be formatted like this. Here we have a row, and vertically we have columns. Now, most NumPy arrays are going to have restrictions. Let me list some of them. Starting with the first restriction. All elements of an array must be of the same data type. Here we created a vector of type integer. All of these are integers. And I'm going to remove the matrix for this example, because I want to show you what happens if we were to insert a string or a character such as x. This will still run, but it's going to implicitly convert everything into a compatible data type. So now everything inside here is the same type as x. Otherwise, if you were to add a float, such as 6.6, it's going to convert every data type into a float, because once again, all the data must be of the same type. Moving on, once you've created an array, the total size of the array can't change. So here we have an array that contains 6 elements. If you want to change the size of an array, you will always have to create a new array. So right now we have a vector here, and if we print it, we get the vector back. But if we want to append some sort of element to it, we're going to have to create a new vector, which will equal a np.append method. And we want to append to our current vector 10 and 20. Then we can print this new vector. And when we run this, you should see that the new vector will contain the new values. But there's no way to append to the original vector. That method does not exist, and you can't remove from it either. Although it's important to mention that we can still modify the array. So if we want to change the value at the index of 3, we can do that. But I'll show you how that's done later. And finally, the data must be rectangular, as quoted from the docs, which means it must have the same number of columns. Otherwise, it's considered to be jagged or jagged. Do let me know in the comment section down below how to pronounce that. When I record, I just forget how things are pronounced. I think it's pronounced jagged or jagged. Anyway, to demonstrate what I mean, I'm going to recreate my matrix, which contains 2 elements that contain the same amount of elements. So here, if we were to print the matrix, you'll see that we'll get this as an output, which is quite nice and convenient. But if one of the items inside our matrix contained less items than one of the other items, NumPy would not understand how to handle this, and it would tell us exactly what we did wrong. Every nested array inside this matrix must have 3 elements, or it's not going to work. So this must have 3 elements. So those were a few of the restrictions that we have with NumPy arrays. And all of these restrictions are used to guarantee the speed and efficiency of the NumPy array. In general, the more specific you are about what you want to do with your data, the faster it will be to perform those operations on it. In Python, the native list type we have is ultra flexible. We can add any type of element to it and as many as we want. But because of this flexibility, we lose a lot of speed and performance. So this was our very first lesson on NumPy. I hope you guys are excited for this series because we have a lot more to learn. In today's video, we're going to start learning about array fundamentals. In the previous video, we saw that we could initialize an array using a Python sequence such as a list of integers. For example, we might have an array which will equal a NumPy array, and inside here, we'll just pass in a sequence of integers. And when we run this, what we're going to get as an output is a one-dimensional array. In NumPy, we have various ways to access elements from an array. One of the most common ways to do so is by using the integer index of the element we want to retrieve in square brackets. So here, in case we want to retrieve whatever's at the index of 2, we can do so by specifying in square brackets 2. And when we run this, we're going to get 3 as an output. In NumPy, arrays are 0 indexed, meaning that the first element of any array will always start at the index of 0. Now, in the previous lesson, I told you that arrays could not change in size, but that doesn't make them immutable. We can still change the elements at any given index. For example, array at the index of 2 can now equal 999. And now when we print this array, what we will get as an output is 1, 2, 999, 4, 5, and 6. So we can still modify an array. We just can't append to it or remove from it. Also, just like with a Python list, you can use slice notation in NumPy. So we can grab all the elements from 3 onwards using this syntax. And as an output, we will get 4, 5, and 6. Otherwise, we can step 2, or we can also check what's between 1 and 3. And when we run this, what we should get back is once again 4, 5, and 6. For this part here, we're using a step of 2, so we will get 1, 3, and 5. And the last one is going to return to us 2 and 3, because that's what the slice of 1 to 3 refers to. One major difference though is that slice indexing of a native Python list returns a copy, while in NumPy it returns a view, which means the slice will still refer to the original array. So first I'm going to show you how it works in Python so that you can see the difference in NumPy. So here we'll create a PyList, which will be of type integer, and that will equal 1, 2, 3, 4, 5, and 6. Then right below that, we will create a PySlice, which will be a list of integer, and here we'll type in PyList and grab everything up until 3. Now, if we were to change our PySlice by typing in PySlice at the index of 0 equals 999, and of course you can't print this, silly me, but if we were to change that element and then print the PySlice, you'll notice that our slice is going to contain 999 as the first element. And something else that you'll notice is that the original list will remain unmodified. So we'll type in print PyList, and when we run this, it will still contain the values of 1, 2, 3, 4, 5, and 6. So this slice over here is an independent copy. Now watch what happens when we attempt to do the same thing with a NumPy array. So here we'll create an array, which will equal a NumPy array, and we'll pass in the values of 1, 2, 3, 4, 5, and 6. Then we'll create a slice, which will equal the array from 0 to 3. Now we will refer to the slice and say that at the index of 0, we want to replace that value with the value of 999. Then we will print the array slice. And as an output, we will get 999, 2, and 3. So far, everything's exactly the same as when we did this in Python, using the native list type. But now watch what happens when we print the original array. You'll notice that the original array was modified, because here we did not create an independent copy. We created a view. So we are just viewing this data, but this data still refers to the original array. And that's why when we try to modify something within it, it modifies the original as well. Moving on, if you want to initialize an array with 2 dimensions or higher, you can do it via nested Python sequences. For example, you might have a matrix, and that will equal an array with a nested list of 1, 2, 3, 4, 5, 6, and 7, 8, and 9. And here we have an undercover period, which we're going to replace with a semicolon, and everything will work fine. Now, when we print this, what we're going to get as an output is this matrix over here. So here we have an array of 2 dimensions. Now, the dimension of an array will sometimes be referred to as an axis. You'll see why this terminology can be useful down the line as we learn more about NumPy. In NumPy, we also have some special syntax that we can use to access an element in a multi-dimensional array. This requires us to specify the index along each axis with a single set of square brackets. For example, I'm just going to open up the terminal because right now we have a very nice representation of our data. And what we want to do is access this element over here. So the way this works is that we need to refer first to the row, which is the first axis, and then to the column, which is the second axis. So to refer to 6, we need to type in matrix at the row, which is at the index of 1, and the column, which is at the index of 2. So here we have the row at the index of 1, and the column, which is at the index of 2. So when we run this, what we will get as an output is 6. And I believe we can also format this like this. Nope, it just put it all back. Maybe in PyCharm it works, I have no idea. I thought it would maintain the form, but Z absolutely refused that. So I'm just going to reprint the matrix so that we can see it once again. Now, if we want to refer to the 8th element, we're going to have to count downwards. So 0, 1, 2. So the first index is going to be 2. And then we need to count which column. So here we have 0 and 1, which means all we need to do is insert 1. And this will refer to this element over here now. As you can see, when we run it, we'll get 8 as an output. And there's one last thing I want to mention before we conclude today's lesson. Throughout your programming career, you might hear the following mathematical terminology. A 0-dimensional array being referred to as a scalar, a 1-dimensional array being referred to as a vector, a 2-dimensional array being referred to as a matrix, and a multi-dimensional array being referred to as a tensor. And here n is just any number that's greater than 2. The NumPy documentation states that it's best that we avoid these mathematical terms when working with NumPy arrays, because the mathematical version does not translate perfectly into the NumPy version. Even if the name is technically correct, the operations might be different than the ones you perform in mathematics. For example, matrix multiplication is going to be fundamentally different than array multiplication. And these names are also widely used in other libraries, such as in PyTorch, where the fundamental structure is in fact a tensor. So from this point forward, I will do my best to be as clear as possible and not use these terms that frequently. But in case I do, just know that I'm referring to arrays in NumPy, and not to anything related to math or other Python libraries. If I perform matrix multiplication in a future video, I will be extra explicit about which one I'm using. The whole reason I'm mentioning all of this is because I'm human and I make mistakes, and sometimes I will refer to a 2-dimensional array as a matrix or a 1-dimensional array as a vector. The NumPy documentation discourages us from doing that, but again, I'm only human and I make mistakes sometimes, so I just thought I would put that disclaimer on the video. Next, we're going to continue learning about some important and fundamental attributes of a NumPy array, and also how to create an array with ease. So let's start by creating a 2-dimensional array. So here we'll type in array, which will equal an NP array, and inside here we'll type in 1, 2, 3, and 4, 5, and 6. That was very poorly executed. Now when we print this array, what we should get as an output is this array over here. If we want to access the amount of dimensions of an array, we can do so using the array attribute. So here I'll type in dimensions and pass in the array.nDimensions, which is the number of dimensions attribute. And when we run that, we'll get 2 dimensions back, because this is a 2D array. If we only had 1, 2, and 3, which is of a single level, we will get 1 dimension back. Next, we have the shape attribute. So here I'm going to change this to shape and pass in shape here. And what this does is return to us the shape of the array. As you can see, we have a 2x3 array. And what this means is that we have 2 rows and 3 columns. Otherwise, we can also get back the size by referring to the size. And here we're going to get a size of 6 back, which is the total number of elements in this array. And finally, we can get the type of the array back by typing in dtype. And that's going to return to us the type of int64, because all of these are integers. And we can make this more specific by typing in dtype and passing in np.int16 if we know that these integers are going to remain relatively small. And the next time we refer to the dtype attribute, we will get int64 as an output, because that's what we specified in the original array. Moving on, let's look at some of the special methods we have for creating new arrays that don't require us to manually type out the data. Starting off with zeros, which will equal np.zeros. And here we want to fill it with 5 zeros. Next, let's print it to see what happens. And when we run this, you should notice that we will end up with an array with 5 zeros. And if we print the d type, it's going to tell us that each element is of type float64. But what's cool about this method is that we can also specify this to be of different dimensions. So here, instead of passing in 5, we can say we want 3 rows of 5 elements. And we can also specify the d type to be of type integer. Now the next time we run this, we will get 3 rows that contain 5 elements each. And the type will be of type int64. And you can do the exact same thing with ones. And we should rename this to ones, so this makes sense, and then rerun the program. And this time we're going to end up with a matrix of ones. And you're not limited to inserting an array of 2 dimensions. You can even pass in an array of 3 dimensions. And just like that, we will end up with a 3-dimensional array. Up next, I want to talk about a method which is called empty. And empty creates an array with random content which depends on the current state of the memory. The reason to use this over zeros or other similar methods is for speed. np.empty is blazingly fast. So here we're going to type in empty equals np.empty, and we want this to contain 5 elements. Now when we print empty, what we should end up with are these 5 random elements. We can also do it using a 2-dimensional array, and just like that, we will end up with this over here. And once again, you can never rely on what content this generates. It depends 100% on the current state of memory. So in this example, it might produce this matrix 100% of the time, but you cannot rely on this because if the state of the memory changes, this is going to change. Moving on, let's talk about a range, which is used for creating ranges. And I've read this as a range so many times, but it's a range. So here we're going to print np a range and pass in 10, which will create a range from 0 to 10. And 10 is not inclusive, so we're going to end up with the last number being 9. Otherwise, we can specify this to be from 5 to 10, and we'll end up with a result such as this one. And just like with most range syntax, we can type in 0 to 20 with a step. And now it's going to step 2 when we generate this range. And finally, the last method I want to cover today is called linspace. If you ever want to create an array with values that are linearly spaced, you can use the linspace method. For example, here we can type in np linspace and pass in 0 to 10. And we want this to be spaced with a number of 3, which means it's going to create a range with 3 elements that are spaced linearly. Now we can duplicate this and pass in 5. And what you'll notice is that we'll get something like this as an output. We have 5 elements that are spaced linearly. Otherwise, we can change this to 20, and we'll get something crazy like this. And all this is an array of 20 elements spaced linearly. And in all the methods I showed you, with the exception of empty, you can specify the data type in case the default one does not satisfy your requirements. So in this case, maybe you want everything to be of type integer. And when you run this, what you'll get back are integers. And they're not really going to be spaced as linearly as if you were to use a float, but it's going to do its best to round them. Otherwise, you can also convert them to strings. Personally, I don't know why you would do that, but it's nice to know that you can change the data type just by specifying it. And if you come from a language like C or Rust, you can get even more specific by referring to np and passing in the data type you wish to insert, such as a float16. Because maybe you don't care about all that precision that float64 gives you. Continuing with NumPy arrays, it's time we learn about how we can add, remove, and sort elements. In addition to all that, we're also going to learn the concept of reshaping arrays. Now, as always, to get started, we're going to create an array, which will be an np.array, and inside here we'll pass in 3, 2, 10, 1, and 0. The easiest way to sort an array is by using np.sort. For example, here we will print np.sort and pass in our array. And this will ascend it in ascending order. If you prefer to sort your array in place, you can do so by typing in your array and sort. Now we can just print the array as it is because this sorted it in place. Also, if you hover over sort, you'll notice that there are quite a few arguments that we can use with sort. That's something that we're going to explore later as we learn more about NumPy arrays. Up next, let's talk about how you can concatenate two arrays. In NumPy, if you ever want to concatenate two or more arrays, you can use the np.concatenate method. So in this example, we're going to create two arrays, one called A and one called B. And what we want to do is put those together. So here we're going to type in np concatenate and pass in A and B. Now we need to pass this in as an iterable. So it can be passed in as a tuple or as a list. That's up to you. But now when we run this, what we should end up with is a new array with all the elements concatenated. And you can even add a third one if that's what you want. So we're just going to call this C, pass it here. Obviously it contains duplicates, but that doesn't matter because when we run this, you'll see that it will concatenate it with the other ones. And this method is quite convenient because even if you have several arrays of different dimensions, such as A, which is a matrix, it's still going to be able to carry out that concatenation. As you can see, we end up with a new matrix that has 10 and 20 appended to the end. Moving on, let's talk about reshaping NumPy arrays using the reshape method. And first of all, let's create an array that contains 10 elements. And this time we're going to use a range to generate 10 elements. And when we print this, what we're going to end up with is this array over here. And I'm just going to call it original so we can keep track of it. But now, if you ever want to reshape an array, all you have to do is use the reshape method and specify the new dimensions. For example, here we'll have array.reshape, and what we will pass in is 2 by 5. So 2 rows and 5 columns. And when we run this, you'll see that we will get 2 rows and 5 columns. And we can also do that the other way around. We can specify 5 rows and 2 columns. And when we run that, we're going to get 5 rows and 2 columns. The rule of thumb here is that you must always have the same number of elements in the new array. To make sure your reshaping is logical, you can calculate the product of the reshaping. Right here we have an array of 10 elements, and here when we reshape it, we have 2 by 5. And the product of this is 10. And the same thing goes for the second one. 5 times 2 is 10. So that gives us 10 elements in total. So as long as both of these equal 10, it's going to work. But if we were to do something such as 2 by 1, that's going to just give us a total of 2, which means we're going to run into an exception. With that in mind, let's create a 3D array using the reshape method. So here we're going to specify 27 elements in our range. So when we run this, we're going to have this array over here. But let's reshape that into a 3-dimensional array. So here we'll print the array, reshape, and we're going to put 3 by 3 by 3. So 3 times 3 is 9, times 3 is 27. So the elements add up, which means this is going to work. So now we can run our script, and what we're going to get as an output is this reshaped array. We can also type in 1, 9, and 3, and since the product of these ends up being 27, it will also work. As you can see, we get this as an output. And once again, as long as the total number of elements in the new shape are the same, you can reshape as much as you like. For example, instead of just reshaping here, what we're going to do is refer to the original array, or not refer to it, but we're going to overwrite it with the new shape. And right now, if we were to run this, we'd get the exact same output that we had earlier. But let's copy and paste this directly under, because even if the array now looks like this, we can still reshape it. We can change it back to 3 by 3 by 3, and this will work just fine, because this array from earlier contains 27 elements, and so does this one. And then we can go right below that, and we can also insert 27 if we want to convert this into a 1-dimensional array. As you can see, it converts it back to what we had at the start. In case for whatever reason you don't know how many elements you have, or you just don't want to type it out, you can also use the -1 shortcut. And this will convert any array into a 1-dimensional array. In this lesson, we're going to learn how to add a new access to an array using some new syntax. Then we're also going to start learning about how we can index and slice NumPy arrays. Let's start off by learning about two useful ways to increase the dimensions of an existing array. The first is done by creating a new access using the new access constant. Here we're going to create an array which is one-dimensional, and that's going to equal a range until 3. And the very first thing we're going to do is check what shape it has. So when we run this, it should give us a shape of 3. This shape tells us that it has only one dimension. Next, let's try to add a new access along the first dimension. And to do this, we're going to overwrite the original array, and we're going to type in array, square brackets, np, new access, and colon. Then right below that, I'm going to print the array and the array shape. So we have all of this information. And when we run this, what we should get back is an array with a new access. As you can see, instead of just 3, we now have 1 and 3 as the shape. If you want to add a new access along the second dimension, you just reverse this. So you add colon, comma, np.newAccess. And when we run this, we will get this as an output. And we will again have 2 dimensions. But we also have another method which I find much easier to read called expand dimensions. And here we're going to type in expanded equals np expand dimensions. And what we have to do here is pass in the array that we want to expand and along which axis we want to expand it. So here we can add an axis along the first dimension. And when we print this, what we should end up with is pretty much what we had earlier, but using this new syntax. Otherwise, if you change the axis to 1, it's going to add an axis along the second dimension. Up next, it's time we cover how indexing and slicing work in NumPy. First of all, you should know that slicing and indexing can be done the exact same way as you do it in Python. So just to demonstrate that, I'm going to change the range to 10. Then I'm going to print the range at the index of 0, the range at the index of -1, the range at the index of 3 to 5, or that's actually a slice. Then we can also step 2 by using this syntax over here, and so on. When you run this, you're going to notice that it works exactly the same way as it would in Python. And I'm not going to cover all the ways you can index and slice lists in Python because this is a NumPy tutorial. So we're going to immediately move on to what makes slicing and indexing unique in NumPy. Now let's delete all of this and replace it with this matrix. One cool feature we have in NumPy is being able to specify a condition for the values we want to get back. For example, we can print the array at the index of only the even numbers. So here we need to write a formula that grabs the even numbers. And we can do that by specifying the array modulus operator 2 equals 0. We wrote the condition for the elements that we want to get back. And when we run this, we should end up with all the even numbers. Otherwise, if we duplicate this, we can also check for all the values that are less than 3. And if we run that, we will get 0, 1, and 2. So it grabbed these values. Or we can also check for all the values that are greater than 10. So we can add greater than and 10. And we should end up with 30 and 40. So it's quite cool that you can specify conditions for the elements you want to get back. And we can even specify multiple conditions. And to demonstrate that, I'm going to change this back to a range with 20 elements. And we're going to print the array at the index of array where every element is greater than 10. And note that I'm doing this in parentheses because we're using the logical AND operator here so that we can combine conditions. And where the array, or the elements in the array, modulus operator 2 are equal to 0. Just like that, we were able to combine multiple conditions for the elements we wanted to get back. So now when we run this, we will get 12, 14, 16, and 18, because all the elements here are greater than 10 and are divisible by 2. Or in other words, those are even numbers. And this also works with the pipeline, or the logical OR operator. So here we're checking that the array modulus operator 2 is equal to 0 for even numbers, or that the array is equal to 15. Not the array, but the element. And now when we run this, we're going to get 0, 2, 4, 6, 8, and so on, all the even numbers, plus 15, because these were the conditions we specified. And only one of these had to be true for it to return its value. And I'm just going to copy this right here because you can also use logical operators to return booleans based on the conditions. So let's remove this. And what I'm going to do here is type in conditional, and we're just going to paste in this condition. And now when we print this variable, what you'll notice is that we're going to get back an array of booleans where this condition was met and where it was not met. So instead of getting the actual value back, we're getting the boolean back on whether it met the condition. If you want to retrieve the indices of the values that meet your condition, you can use the non-zero method. So here what we're going to do is create a matrix which will equal np array, and we'll pass in 2, 3, 3, and 4, 4, 6. Right now when we print this matrix, it's going to look like this. Now to get back the indices of the condition we specify, we can type in print np non-zero, and inside here we'll add the matrix modulus operator 2 is equal to 0. So we're checking for all the elements that are even. Now when we run this, what you should notice is that we will get back two arrays. One that's going to specify the row and one that's going to specify the column. And what it's saying here is that on the first row, at the index of 0, we have an element that meets the condition, 2. Then, on the second row, right over here, we have an element at the index of 0 that also meets this condition. And that's true for 1 and 2. As you can see over here, everything refers to the second row. If we were to check for odd numbers, we're going to get a different result here, since we only have two odd numbers. As you can see this time, each array only contains two elements, or two indices. So once again, on the first row, which is this one over here, at the index of 1, we have an odd number, which is number 3. And we also have the same thing over here, which is at the index of 2, still on the first row. But what happens if you have no elements that match? So matrix, where the element is equal to 100. Well, if the condition is not met by any of the elements, you're going to get this as an output, an empty array, and the type that it contains. It's time we learn more about how we can create arrays from existing data. Imagine you have this array, which will equal an NP A range, which goes up to 10. You can create a slice from this array using the following syntax. Array slice equals array from 3 to 6. Next, we're going to print the array, which will equal the array, and the array slice, which will equal the array slice, so that we can see them side by side. Right now, if we were to run this, we'd get back the original array and the array slice. Here's an important detail though. When you slice a NumPy array like this, you're actually creating a view of that slice, not an independent array. This means that any changes to the slice will also affect the original array. And this behavior can be quite surprising if you're expecting a completely separate copy. So just to show you what I mean, I'm going to type in array slice at the index of 0 equals 999. Then I'm going to copy this and paste it directly under, so that when we run this, you'll see the changes. Here's the slice that we thought was independent when we created it, but as you can see, as soon as we change something in our array slice, which is just a view, it also affects the original array. And most programming languages do this to optimize performance. Copying data is considered to be an expensive operation, so many languages require you to be explicit when you actually want to copy the data. And we'll come back to this in just a bit so I can show you how you can actually create a copy in case that's what you want. But next, let's take a look at how we can stack arrays in NumPy. So to get started, I'm going to create these two matrices so that we can use them for the example. And the very first thing we're going to do is stack both of these horizontally. So to do that, we'll type in np hstack and pass in A and B. And when we run this, what you should notice is that we will end up with a matrix such as this one. It stacked them horizontally. And just like with hstack, we can use vstack, which will stack them vertically. It's as simple as that. Now going back to the first example where we created a slice of data from an array. As I mentioned earlier, what we did is create a view of the original data. So here if we type in array equals np a range and pass in 10 once again, and then type in array slice just like we did earlier, and say that that's an array slice from 3 to 6. And then at the index of 0, we change it to 999. Once again, if we print this data, we're going to notice that this operation over here affected both of the arrays, because once again, this is just a view. It did not copy that data, even if in vanilla Python, it would copy it. And once again, the reason NumPy creates a view is because it saves memory and is much faster than copying the data. If you actually want to create an independent copy, you can use the copy method, which will create a deep copy of your data. And to do that, you just need to add the copy method to whatever array you want to copy. So here we're creating a view and then we're copying it, which means that when we try to change an element in the array slice, it's only going to affect the new array and not the original, because now we're working on a deep copy. Each one of these arrays are unique. And just note that this one behaves differently than the one that's built into Python, because the one that's built into Python performs a shallow copy, while in NumPy, it performs a deep copy. Moving on, we're going to start learning about array operations and one of the coolest concepts in NumPy called broadcasting. Let's start this lesson off by creating two arrays. The first one's going to be called first, because my imagination is wild, and that's going to contain 1, 2, and 3. Then the second one is going to be called second, and this will contain the values of 4, 5, and 6. Next, let's try to add both of these together. So here we're going to print first plus second, and what we should get as an output is the data being added together element-wise. And what that means is that 1 was added to 4, 2 was added to 5, and 3 was added to 6. So that's how we ended up with 5, 7, and 9. This also works naturally for all the other operators. And to demonstrate that, I'm just going to duplicate this a few times. And I'm going to add the subtraction symbol, the multiplication symbol, the division symbol, and the power operator. And when we run this, what we should get as an output are all of these operations being performed element-wise. So for subtraction, we're subtracting 4 from 1, 5 from 2, and 6 from 3. And that gives us -3 for each one of these operations. Then it does the same thing for multiplication, division, and also when it uses the power. But we can also use special methods to get the sum of arrays of any dimensions. For example, here we might have a matrix, which will equal a NP array, and that's going to contain 1, 2, and then 3 and 4. Right now, if we were to print this matrix, we would end up with this matrix over here. If we were to print the sum of this matrix, what we would end up with is the sum of 10, because it added all of these elements together. Optionally, we can also specify an axis. If we specify the axis to be 0, it's going to add the elements vertically, so 1 plus 3 and 2 plus 4. If we specify the axis to be 1, it's going to do it horizontally, so 1 plus 2 and 3 plus 4. And we can also do this with multiplication by using the product method. So right now, if we were to run this, we would get 24 as a product, because 1 times 2 is 2, 2 times 3 is 6, and 6 times 4 is 24. But again, we can specify an axis, such as the axis of 0, and it will multiply it vertically. Up next, it's time we talk about broadcasting. There are going to be times when you're going to want to perform operations between arrays of 2 different sizes. For example, we might have some data, which will equal NP array of 1, 2, and 3. And we might want to multiply each one of these elements by 3. So to do that, we're going to create a multiplier, because this can be any number, which will be of type integer, and we're going to insert 3. Next, we're going to print the data times the multiplier. And obviously, you did not have to create a whole new variable for this. You could also just insert 3, and that would work as well. But when you run this, you'll notice that it multiplied each element by 3. And then it returned to us a new array with the result. If we change this to 4, it's going to multiply each element by 4. Even if the data has more dimensions, such as this matrix over here, which will contain 1 and 2, and 3 and 4. NumPy will still understand how to multiply this. It will multiply each element in this matrix by 4. And the NumPy documentation defines broadcasting as a mechanism that allows NumPy to perform operations on arrays of different shapes. The dimensions must be compatible though, otherwise you will get a value error. For example, we're going to use the same data over here, but this time we're going to pass in a 2D array that contains the values of 2 and 3. Or to be honest, we need to change this to a NumPy array first and remove this type annotation. Now this is going to work because the dimensions are compatible. As you can see, when we run this, it's going to be able to multiply 1 by 2 and 2 by 3. Then on the next one, it's going to multiply 3 by 2 and 4 by 3. And that's how we ended up with this result. This makes sense to NumPy. We have exactly 2 elements to multiply for each element in the original NumPy array. Now, if we were to add a third element in here, this would no longer make sense to NumPy, because right now we're multiplying 1 by 2 and 2 by 3, but what are we going to multiply by 4? There is nothing to multiply there. For this to work, each element in the original data is going to have to contain 3 elements. Like that. Then it will work. But if we multiply it like this, it's going to raise a value error, because the shapes were incompatible. Now, before we conclude today's lesson, there are a few more useful operations that I'd like to cover. So for our next example, I'm going to create an array of ages. And you'll probably see these being used a lot in NumPy, and they are all quite straightforward. So the first thing we're going to do is refer to ages and get the max value back for the ages. And right below that, we're going to get the min back. Then we're going to get the sum, the mean, the product, and the standard deviation. Now, when we run this, we're going to get a lot of useful information back. The first value is going to be the maximum value in the array. The second one will be the minimum value in the array. Sum is going to return the sum of all the elements in the array, which is going to end up being 216. Then for the mean, we will end up with 27, and this returns the average of the array. Then we get the product of all the elements of the array when we use the product method. And finally, we get the standard deviation using the std method. So that was quite straightforward with a simple array. But let's create a matrix that's a bit bigger. So here we will create some data, which will equal an NPA range from 1 to 17, and we're going to reshape that into a 4x4 grid. Now, when we print this data, it's going to look like this. First of all, we're going to print the max value of this data. So data.max. And when we run this, what we're going to get as an output is 16. But something else we can do is specify an axis. So what I'm going to do is duplicate this twice and specify an axis for each one of them. So axis 0 and axis equals 1. Now, when we run this, what you should notice is that by defining an axis, we're getting the max value for each column when it is set to 0. When we set the axis to 1, we're getting the max value for each row. So that's how we ended up with these 2 arrays. This is the max value of each column, and this is the max value of each row. And you can choose an axis for each and every one of these methods if that's what you want to do. By specifying the axis to be 1 for each one of these methods, it's going to know that we're requesting the data back from each row instead of from the whole matrix. If we change the axis to 0, it's going to know that we want the data back from each column. I know that we've created many matrices in NumPy by this point, but we're going to start this lesson off by learning a bit more about them. By now, we know that we can create a matrix simply by passing in a nested Python list, and NumPy will convert it to a 2D array. For example, we can create this in Python, and as you can see by this type annotation, this is a list of integers. And all we need to do to create a matrix is pass it into the NumPy array constructor. When we print the NumPy array, what we get as an output is a matrix with some really nice formatting. If we were to print the Python matrix without NumPy, we'd end up with a regular list of lists. Now I'm going to change this to data, which will just create the matrix immediately inside the array constructor. And what we're going to talk about next is indexing and slicing. Indexing and slicing a matrix might seem intimidating at first, but you will get the hang of it quite quickly. Right now, let's just print the data so we can see what we have. And when we run this, what we should get back is this matrix over here. And then what we want to do is grab the first element. So here we're going to type in data at the index of 0. And what that's going to return to us is actually the first row. So by default, this refers to the row. If we were to refer to 2, it would grab this row over here. And just to make this look nicer, I'm going to print selected. So in the console, we can see what we've selected. Or to even make it look nicer, we can just add the data here. Now we're talking. But if you want to grab a specific element, you start by referring to the row and then to the column. So let's pretend we want to grab element number 4. What we have to do here is specify the second row and the second element. So data at the index of 1, 1. And that's going to return to us 4, because this is at the index of 1, and the first column is also at the index of 1. If we type in 2 and 0, it's going to return to us the element 5, because this is at the index of 2, and this column is at the index of 0. So when we run this, we're going to get 5 as an output. Now, slicing matrices follows the same concept. And for this, since it's going to look messy, we're going to create a new print statement. Print data from the index of 0 to 2. Now, when we run this, it's going to select the first 2 rows. If we insert 1, 2, 3, it's going to return to us the last 2 rows. And we can also select which column by specifying it after. So here if we insert 0, it's going to return to us 3 and 5. Here we're telling NumPy that we want to retrieve these 2 rows, and 0 is telling NumPy that we want to retrieve the first column, or the elements from the first column. And that's how we ended up with 3 and 5. Moving on, we're going to be talking about some operations involving matrices. And for this example, I'm going to create 2 matrices, which are called D1 and D2, because in my head, I thought of this as data 1 and data 2. And this is what the data looks like. D1 contains a matrix with these elements, and D2 contains a matrix with these elements. As I showed you in the previous lesson, once you've created matrices, you can use arithmetic operators on them, as long as they are of the same size. For example, if we want to add these together, we could type in D1 plus D2. And when we run this, we should get the sum of both of these matrices. So 5 plus 1 gives us 6. Then we get 6 plus 2, which gives us 8. 7 plus 3, which gives us 10. And 8 plus 4, which gives us 12. And you can do this with the other operators as well. Now, if they are not of the same size, for example, if we have one array that looks like this and another array that looks like this, the broadcasting rules will apply. So when we print D1 plus D2, what we're going to get as an output is 100 and 200 being added to each and every one of these. Once again, this will not work if we have 3 elements here. These shapes are not compatible. Next, I want to talk a little bit about generating numbers. In NumPy, we have a few special methods that allow us to create matrices much faster. We already went over these earlier, but I just thought it would be a good idea to cover them one more time. First of all, let's create a matrix of zeros. And to do that, we just type in np zeros and specify the dimensions, 2 by 2. And we can do the same thing with ones. But in this example, I'll do a 3 by 3. And when we run this, what we should end up with are these 2 matrices. But what if you want to create a matrix that contains random numbers? Well, to do that, we need to create a random number generator. So here we'll type in RNG, which will equal np.random.default_RNG. Then we can print rng.random, and inside here we're going to pass in 4 and 3. Now when we run this, we're going to end up with this matrix that contains all of these random numbers. And random number generation is an essential part of NumPy. It is something that's definitely worth getting into in depth. NumPy makes it very easy to generate random numbers. With the random number generator we created earlier, we can also generate random integers. To do so, we're going to type in RNG integers, and we want the integers to range from 0 to 10. Then the size is going to be a 2 by 5, and the endpoint is going to be set to true because we want 10 to be inclusive. Now when we run this, what we will end up with as an output is this matrix over here with a size of 2 by 5. As you can see, the elements range from 0 to 10. If you set endpoint to false, 10 is going to be exclusive, so you will only get values from 0 to 9. I'm not going to dive any deeper into random number generation in this lesson though. I will create a dedicated lesson in the future. In this video, we're going to learn more about NumPy arrays, starting with how we can get unique items and counts back from any array. For this example, we're going to create an array that contains a couple of duplicates. Next, we're going to print np unique and pass in the array. This will give us back the unique values in this array. If you want to get the indices back of the first occurrences of each unique element, you can use the following argument. Return index and set that to true. Now, when you run this, you're going to notice two arrays in the console. One that contains the unique elements and one that contains the indices of the first occurrence of each unique element. So 1 was present for the first time at the index of 0. Then 2 was present for the first time at the index of 2, and so on. If you want to get each array back separately, you can unpack them. So here what I did is create two variables, one called unique and one called indices. And then I assigned it the result of this operation over here. Then right below, I decided to print them with some nice labels. So now when we run this, what we should get back are the indices and the unique values. You can also get the total number of occurrences of each element using the return counts argument. So here we'll type in return counts and pass in true. And when we run this, it's going to tell us exactly how many times each element was present in our array. And this is returned in the same order as this one over here. So 1 has 2 occurrences, 2 has 2 occurrences, and 6 has 1 occurrence. The indices match on both of these arrays. What's nice about the unique method is that it also works with a 2D array. So in this example, we might have a matrix which contains some duplicate elements. As you can see here, we have 2 1s and 2 7s. Now, when we run this code, what we're going to get as an output is this matrix over here. But if we were to print what was unique in this matrix, then we would get this as an output. 1, 2, 3, 4, 5, 6, and 7. Those are the unique elements in this matrix. Now I'm going to leave the original matrix here for reference because next what I want to show you is that we can also specify the axis. So let's print np unique and pass in the matrix and use the axis argument and set that to 0. And for the second one, we will set it to 1. Now when we run this, what you're going to notice is that we're going to get back 3 matrices. And considering that each and every one of these columns and rows are unique, it's just going to return the full array for both of these. So let's modify the matrix to contain 2 rows that are the same and 2 columns that are the same. And to achieve this, we have to type in 1, 1, 2, 1, 1, 2. So now we have 2 rows that are exactly the same and 6, 6, 7. And that gives us 2 columns that are the same. So now when we run this, you're going to notice a slightly different output. Here we have the original array, which contains 1, 1, 2, 1, 1, 2, and 6, 6, 7. Now when we set the axis to 0, what we get as an output is 1, 1, 2, and 6, 6, 7. Because as you can see here, 2 rows are the same. So this is the unique value. Then when we set the axis to 1, we now work with the columns, which means we're going to get this as an output. And here, since we have 116 and 116, which are the same, it removes one of those and gives us this as an output. So once again, you can specify the axis to choose whether you want to work on rows or columns. Moving on, let's explore the concept of transposing and reshaping matrices. Earlier, we learned that we can easily reshape an array by specifying a new valid shape. In this example, I created some zeros, then I printed it, and finally I reshaped it with a new valid shape. This gives us an output of 10 elements, so the rule of thumb was that this product has to also equal 10 if we want this to work. Now when we run this, what we will get as an output is our data being successfully reshaped. And we can also change this to 1 by 10. As long as the result of the product is 10, this is going to work. But now imagine that all you want to do is switch these back and forth. So 5 becomes 2 and 2 becomes 5. Having to specify these values manually each time you want to reverse or change the axes is damn annoying. So what we're going to do instead is use a method that practically does the same thing as what we did right here. And to achieve that, we're going to type in transpose. Now when we run this, it's going to transpose the shape. And what's nice about this is that we can type in data equals data.transpose, print that data, and then we can transpose it immediately after. And this will work indefinitely. As you can see, it moves back and forth. And we can even do this a third time. And it will continue to change the shape from one to another. I mean, something nice to do would be to print the data.shape on each one of these so that you can see that as well. Now when we run this, you'll notice that first it changed it to a 2x5, and then it changed it to a 5x2. It switches those. That's what transpose does. And if you're feeling extra lazy, we also have the most convenient letter in the universe that we can use directly on the array we want to transpose. This is the letter T, which stands for tractor. I'm just kidding, it stands for transpose. And to use it, all we need to do is type in T and T. And as you can see, it does the same thing. Today, we're going to learn how we can reverse an array. And then we're also going to learn more about reshaping and flattening multi-dimensional arrays in NumPy. First of all, let's look at how we can reverse any array in NumPy. So, as always, I'm going to create my NumPy array, which is going to equal np arange and pass in 10. To reverse it, we will use the flip method. So here we can print np flip and pass in the array. And as an output, what we should get is the array reversed. And this also works with 2D arrays. So here I will create an arange and reshape that to 3 rows and 4 columns. Now when we run this, what we should get as an output is a matrix that has been reversed. Just to make this easier to understand, I'm also going to print the original array, because next I want to talk about how you can reverse only the rows or columns. And as usual, to do any of that, you need to refer to the axis, which here we're going to set to 0. So now when we run this, what you should notice is that all of the rows were reversed, but none of the columns were reversed. Here we have the original, and here we have the matrix that was flipped. And once again, each row was reversed, but the columns stayed in place. Now, if you want to flip the columns, you can do so by specifying 1 as the axis. This time, the rows are going to stay in place, but the columns are going to be reversed. Now, if you want to get even more specific, you can specify which row or column individually. Here we're going to type in array at the index of 2 will equal np flip and pass in the array at the index of 2. Then we're going to print the array. And what you're going to notice is that the only row we reversed was the row at the index of 2. Everything else stayed the same. Now imagine you want to reverse the second column, which means we want 1, 5, and 9 to become 9, 5, and 1. Well, to do so, we need to specify that column. So we're going to ignore the row by adding a colon here and then passing in the column number, which is going to be at the index of 1. And we need to do the same thing here. Now, when we run this, what we will end up with is 9, 5, and 1 in the new array. That was the only part we flipped. Up next, let's learn about 2 popular ways to flatten an array in NumPy. For this example, I'm going to create an array of 1s, which will be of type integer. Now, when we print these 1s, what we should end up with is a matrix of 1s. To flatten this, all we need to do is type in 1s and flatten. Then we will end up with a flattened array. What's nice about this is that no matter how many dimensions you have, it's always going to flatten it to a 1-dimensional array. Also, when you flatten an array using flatten, it creates and returns a new copy. So modifying the flattened array will not affect the original. Here we can type in something called new ones, which will equal ones.flatten, and we're going to modify it by typing in new ones at the index of 0 equals 999. Right below, we're going to print ones and new ones. And when we run this, you're going to notice that it did not affect the original. This change was only applied to the flattened array. Otherwise, if you want to save memory and you don't mind working with a view of the original data, you can use the ravel method, which does the exact same thing but returns a view instead. So instead of flatten, we'll just type in ravel. Now when we run this, you'll notice that any changes to the new array will affect the original. So flatten returns a deep copy and ravel returns a view. We've finally made it to the final lesson of this NumPy tutorial series. In today's lesson, we're going to learn how we can save and load NumPy objects, because at some point, you're going to want to be able to load data without having to rerun all your code. Imagine you performed a lot of time-consuming operations that gave you some important data that you wanted to save for later. In this example, we're going to pretend that this is that data. We worked hard for this data, so now let's save it. In NumPy, if you ever want to save an array, you can use the save method. And here, all you need to do is provide a name, which I'm going to call npdata, and the data that you want to save. Now, when you run this, you're going to notice in your project directory that you're going to have a file called npdata.npy, and that contains the array information. To load this data, all we need to do is create a variable, or you don't need to, but I would recommend it so you can use it later, and type in npload. And here we need to refer to that file by typing in npdata.npy. Right now, this is conveniently in the same directory. Otherwise, you're going to have to specify the path, whether that's an absolute path or a relative path to this file. Then we're going to print loaded. And what we're going to get as an output is the array that we saved. There are other extensions we can use with NumPy files, but using .npy is good because it also stores the shape, the data type, and other information that allows us to correctly reconstruct any NumPy array. If you want to save multiple NumPy objects, we can use saves or save-z. So for this example, I'm going to create two arrays, and then I'm going to use np.saves and pass in multiple np as the file name. Then you just need to pass in the objects you want to save, such as array1 and array2. Now when we run this, once again, in your file directory, you're going to notice a new file called multiple np.npz or npz. But this time, when we try to load it, it's going to behave a little bit differently. So let's type in np loaded and pass in the file name, which is multiple_np.npz, and this should be load. Then we're going to print loaded. And what you're going to notice is that we're going to end up with an npz file that contains these keys. And that's not really the information we were looking for. I mean, it's very useful because it tells us where we can get the information, but this is not what we wanted. So next, let's duplicate this and type in loaded.files. And this is going to tell us what the files are named in case we want to retrieve that information. Now, to actually retrieve the NumPy arrays, we just need to refer to the keys. So loaded at the key of array_0 and loaded at the key of array_1. And I'm assigning that to these two variable names so that we can print array1 and print array2. And when we run this, we're going to get back the original NumPy arrays. If you'd rather save the data as text, you can also do that by using the following methods. So for this example, I'm going to create some data which will contain this data over here, and it's going to be of type integer. And I'm explicitly typing this out so you can see what happens when we save this information as text. Here I'll type in save text, and this time we're going to type in textdata.txt and pass in the data. Then right below that, we're going to print load text or np.loadText, and we need to pass in textdata.txt. Now, when we run this, what you're going to notice is that we're going to end up with an array of floats. The text file doesn't store the same information as the .npy file does, which means the D type disappeared, and all the other information regarding this NumPy array also disappeared. The benefit, though, of text files is that they are easier to share, even though .npy files are smaller and faster to read. And you can also export this as CSV. So you can type in csvdata.csv and change this to CSV so we can load it. And when we run this, something went wrong, and that's because the name was wrong. CSV data. But it's going to load it exactly the same way as it did with the text file. And when you open up your directory, you'll notice the two new files we have with the CSV data and the text data. And this method actually has a lot of arguments that you can use with it. Unfortunately, we're not going to cover any of this in this video. But with that being done, we've now made it to the end of this beginner NumPy series. I hope you enjoyed it. There's still a lot to learn, but by now you should have what you need to get started with using it with pandas and for creating your own projects. I will continue teaching NumPy on this channel, but not in the form of a series. The videos in the future will be informational and separated. We will probably also build some projects, but the next step for you is to spend some time every day reading the NumPy docs. They are very well written. This whole series was created thanks to them. Anyway, with all that being said, as always, thanks for watching, and I'll see you in the next video.